So I will present you the implementation of the LDA-1 method in ABINIT very quickly. I have 3 slides. So the objective is to improve the description of band gaps, and in the literature a method has been proposed, the name of which is LDA-1, and is described in details in the paper that is written here by Ferreira and al. In 2008. And I just I just detail the spirit of the method, but I can't go into the details. So this method is derived from the Slater-Yannack transition state theory, and especially from the Yannack theorem that say that the derivative of the energy versus the occupation number are equal to the eigenvalue of the constant state with this occupation. And during some algebra, as we say, it can be shown that we can rely the eigenvalue with the ground state with the eigenvalue with minus half electron to a quantity which is written here S alpha, and it can be shown that S alpha is connected with the whole self energy. And then if we calculate, thanks to the Yannack theorem, for example, the difference between the ground state and the state where 1 electron has been removed, we can write like this. So this is more or less the band gap. And it can be shown also, it is shown in the paper of Ferreira, that the quantity Vs that we need to calculate the gap is the difference between the local potential of the ground state and the ground state minus half electron. This is demonstrated in the case of an atomic formulation. In the crystal, it is shown that we must add to this a cutoff function, like this. And in practice, how do this work? So in the PAW data generator atom core that we use, we perform a first calculation with the neutral atom to obtain V0, a second calculation on ion without half an electron that gives us a local potential V minus half. We calculate Vs thanks to this formula times the cutoff, and this gives this potential. And this potential is added in the PAW data files with a new tag, LDA-1 potential. And so you can, in the next generation, in the next version of the JITH XML PAW data files, there are this potential for the 10 elements for which Ferreira gave in his paper the radius to be used for the cutoff. And what is shown is in his paper is that the band gaps calculated within the LDA-1 method is very close to the experimental one. So in ABINIT, Vs is treated as an external potential. So the energy is calculated as the energy of an external potential in PAW. The Hamiltonian is modified as an external potential, either with local potential here and contribution in the dij term, and to be able to perform the calculation, there is a new keyword, LDA-1, a new input variable that must be set to 1. I have just make a test on the indirect gap of silicon. Donc in ABINIT with LDA, we found 0.55 EV, and within the LDA-1 method, 1.25 EV, which is close to the experimental value for the indirect gap. What is the interest of this method, in fact, in the literature, is that been mainly used as a starting point for a GW calculation, because you start from wave functions that somewhere are better wave functions to describe the gap, and so the starting point is better than the Concham ground state wave functions. There are several papers in the literature using LDA minus half like that. Okay, thank you.